excited to share my team's work in developing a novel way to detect ground perturbations during walking by tracking lower limb kinematic states with applications to lower limb robotic exoskeletons. Okay. Falls during walking are a leading cause of injury, long-term hospitalization, and overall loss of independence for older adults. And while there are many different avenues for intervention, our group is specifically interested in understanding how we can utilize wearable, lower limb robotic devices to improve walking balance and reduce the risk of fall. Recent studies have demonstrated the potential for these devices to mitigate fall incidences, with the caveat that they must be able to react to disturbances in balance before the user's physiological response in order to be effective. This means that we need fast and effective ways that we can detect when the wearer is about to fall, that can be implemented in real time with information available on board the exoskeleton. But let's step back for a second and look at what it even means to detect when the wearer is becoming unstable. One of the most fundamental ways to detect perturbations and quantify stability is the concept of marginal stability, which defines a boundary around your feet and projects your center of mass into that boundary. You can then track the center of mass and look for instances where it leaves that boundary, which we would consider to be perturbations. You can try this yourself by standing up and leaving your center of mass outside the area of your feet, and you'll feel yourself starting to fall. So this approach works really well for standing balance. However, it can be challenging to translate into dynamic activities like walking, given the need to define this constantly changing boundary and the need to include velocity vectors into this analysis. Therefore, researchers have turned to another metric as a potential way to detect perturbations during walking. This involves the calculation of whole body angular momentum, which sums the momentum of all your limbs around the center of mass. And this has relevance to stability because humans tend to regulate this value very tightly during steady walking, and we often see spikes in this value associated with disturbances in balance. Therefore, we can use a threshold-based approach to identify spikes in this value and determine someone to be perturbed when their whole body angular momentum spikes above these values compared to steady state. While this works very well for offline analyses, the computational complexity of calculating the whole body angular momentum limits its applications for real-time exoskeleton devices. Furthermore, there's potential for oversensitivity or lack of representation of the way we maintain stability during walking. For example, I can wave my arms pretty wildly while maintaining balance, and so there's a need and a gap for developing or identifying a metric that we can utilize on board an exoskeleton device to detect when the wearer is becoming unstable. It turns out that maintaining stability during walking is actually a lot more challenging than we might give ourselves credit for. However, kinematic states, specifically the position and velocity of the feet and center of mass, provide a lot of important insights into how we maintain this and achieve this task. We can look at the position of the feet relative to the center of mass to understand how we need to modulate our step width and step length to remain stable during walking. And one benefit of these states is that they can be easily tracked in real time using wearable markers or sensors. Velocity states can also give us important insight into how we need to modulate the speed of our feet and center of mass, also to maintain balance during walking. Another important characteristic of these states is that they follow very distinct and recognizable patterns during steady-state walking. However, when we experience perturbations, we can see that they exhibit pretty instant and significant deviations from these patterns. So we can leverage this to detect deviations from stability states and identify perturbations. We hypothesize that a method that tracks these kinematic states will outperform the previously mentioned whole body angular momentum benchmark through, firstly, more accurate detection given the way that kinematic states govern our walking stability, and potentially through faster detection due to minimized computational stability, and also the ability to apply them on-board the exoskeleton. For the purposes of this work, we tracked 16 kinematic states in a coordinate system local to the body using reflective markers, and we're currently working to translate this to wearable inertial measurement unit sensors. For each foot, we tracked 3 positional and 3 velocity states relative to the center of mass, and this takes inspiration from the inverted pendulum model of walking, which is a fundamental model used to understand and kind of demonstrate how humans modulate step width and length and move their center of mass to remain balanced. We also tracked 2 positional and 2 velocity states relative to the center of the feet. So this allows us to capture those important insights from the idea of marginal stability without having to really define that geometric boundary in real time. But how can we actually use these states to detect perturbations? We started with a diverse gate biomechanics and ground perturbation dataset developed by Dr. Jennifer Lisma at Georgia Tech, which has about 96 unique types of ground perturbation across 12 participants. This gives us a very robust and diverse dataset that we can use to develop our model. Our approach starts by tracking gait cycles over time. For the purposes of demonstration, we'll look at the position of the right foot, interior and posterior to the center of mass, for 1 subject and 1 child in the open source dataset. We start with a conservative value of about 10 gait cycles, which we hope to reduce in the future, and we create an additional pattern of a mean and standard deviation to demonstrate what this state looks like during stable walking. And this can be adapted to each individual person by just taking their first 10 gait cycles. We can then track subsequent gait cycles and compare them to this steady state pattern. If they remain within 2 standard deviations of the mean, we'll use them to update the mean over time to account for natural long-term drifts in walking kinematics. However, eventually in this dataset, the person experiences a trip perturbation, and we see pretty instantaneous and significant deviation of these states, meaning they're outside 2 standard deviations of that normal state during steady state walking. To quantify this in a simplified way, we utilize a distance vector that takes the distance between the current state value at the current time point and what the expected value is 2 standard deviations from its steady state mean. We then normalize this distance vector by the mean and standard deviation so that we can sum states across positions and velocities that have different scales and units. This gives us a final equation that looks a little bit complicated, but it's really just the normalized distance vectors across all those 16 states I mentioned earlier, summed together into a single metric that tells us how unstable or how much the stability is deviating from normal patterns. And we divide by the number of states just so we can have a nice value between 0 and 1. And we're calling this our stability deviation metric. You can see here in this graph that we have nice kind of low values during stable walking, and we see that pretty significant and immediate spike in response to perturbation. So that's what we were hoping for. Now that we have this kind of single metric, how can we use it to actually detect perturbations? We considered a slope-based approach or using different signal processing methods. However, analysis determined that magnitude or threshold-based approach would actually be the most optimal, given that it's simplified and the fact that these states deviate really significantly, even in response to small perturbations. We then wanted to ensure that this threshold was generalizable to different subjects and many different perturbation conditions. So we utilized that same open source data set and used a grid search threshold approach to sweep different thresholds, prioritizing thresholds that increase the accuracy of detection, so is this gait cycle perturbed or not, and decrease the delay between when the perturbation actually happened and when we detected it. And we found a value of about 0.125 was that kind of optimal sweet spot. And you'll see we can't quite get to 100% accuracy. In post hoc analysis, we found that some of the perturbations in the open source data set didn't cause significant deviations in stability, so we believe that's one of the reasons, and we'll see further evidence in our further analysis. To determine the overall generalizability of this threshold and this approach overall, we conducted a pilot study where we executed this method in both offline and real time, using that same threshold optimized only on the open source data set. We had 5 healthy subjects who experienced intermittent trip and slip perturbations during steady-state walking via changes in treadmill belt speed. And these occurred at different stages in the gait cycle to get a more representative perturbation response. Here is a representation example of what it looks like to detect a perturbation in real time. So we're calculating those difference vectors and we're looking for this spike above the threshold. We were also able to utilize this method to determine the direction and magnitude of perturbation by looking at those positional changes and velocity changes post-op, which we hope will be applicable to exoskeleton control. Overall, we saw a 98.8% accuracy in detecting perturbed gait cycles. And as you can see, we have this increased accuracy from our performance on the open source data set, likely because we chose a bit more aggressive perturbations. We also were able to detect perturbations about 47% higher than the whole body angular momentum benchmark that we mentioned earlier, due to a lot of kind of false detections of the whole body angular momentum method. We also found that we were able to detect perturbations within about 230 milliseconds, which is actually faster than the average older adult stepping response, so the time it takes to execute a stabilizing step in response to a perturbation. So this is exciting in terms of our applications to exoskeleton control and overall development. And lastly, while we detected 100 milliseconds slower than whole body angular momentum approach, this does not include computational time, which would definitely spike that value. Overall, we were able to come up with a successful method, and we were looking forward to applying it with wearable sensors and eventually providing assistance to perturbations in response. And thank you to everyone that helped me and supported me on this project.
Any questions? Please come up to the mic if you have any questions.
Yeah, I got a question. So did you, because you used the data sets, were you able to identify what's a false alarm for your detection?
Yeah, so in the data set, we knew the exact time of perturbation, so we were able to distinguish ourselves which cycles would be perturbed or not, and then use that as our metric of is this a false detection or not, if that makes sense. Because we knew that only one perturbation happened per trial.
But do you have the accurate or the value of false alarm rates?
Oh, so it was a total. So if you subtract 100 from 47, so about like 53% of the time, we saw those false detections, given the threshold stated in some previous literature.
Hi, good talk. I was wondering if, so you mentioned that in some of the conditions there is very little instability due to this, and I was wondering, do you have any thoughts on how you might approach detecting perturbations in which there aren't large schematic changes, and if those are even worth detecting?
Yeah, so I think one of the findings that we had is that in the future, it might be more beneficial to use a range rather than a single threshold, so that we can get more information. Because even though for healthy adults, those small perturbations might not have affected their stability, for older adults, those would likely be a problem and cause falls. So reducing the sensitivity or having some sort of like more range might provide us more information for exoskeleton control, where we can provide assistance depending on kind of that range of stability versus just a binary, are you going to fall or not? And that might be more helpful for those situations.
Okay, really quick.
Sure, yes, this will be quick. I was just curious, when you were figuring out the threshold, did you consider scaling it for different participants, or just, I don't know, I'm just curious if you consider that?
Yeah, we tried to just keep it as generalizable for now, so we just did the threshold across all participants, and we're able to then apply that to all subjects. But in the future, some personalization might be beneficial.